This is lecture 18.3, and it's going to be taking a look at spontaneous reactions. When a lot of people think of the word spontaneous, they think of something that happens readily or something that happens immediately. And that's sort of the definition of what a spontaneous reaction is in chemistry, but it's slightly different. So we're going to take a look at what a spontaneous reaction is. We're going to compare that to a non-spontaneous reaction. So in simple words, a spontaneous reaction in chemistry is a reaction that happens or occurs. Now, I can create a chemical formula on paper. However, that doesn't mean that the reaction is actually going to take place. So that would be an example of a non-spontaneous reaction, and this is something that doesn't happen. So non-spontaneous reactions, they don't happen. I'll give you an example of a non-spontaneous reaction. So there are two factors that define a spontaneous reaction, whether a reaction will occur or not. And the first factor is entropy, which we have not discussed before. And we also have heat, which we have discussed. We've discussed endothermic and exothermic reactions. So we're first going to take a look at this concept of entropy. We'll take my house, for example, or your bedroom, but give you a glimpse of what happens inside our house. Kids come home from school on typical days. Their backpacks are left at the front door. Their shoes are not put in their shoe box. Their socks end up in the middle of the living room. They start working on one activity at the breakfast nook table, and then they go to play outside, and they come back inside, and then everything just turns into chaos. So this is actually a good example of entropy. Maybe your bedroom is the same way. Is your bedroom right now perfectly clean? Is the bed made? Is everything put in the closet? Is everything that's under your bed in the appropriate place? So entropy is chaos and disorder. Chaos and disorder. This is the tendency for things to go into entropy. Things tend to go into this state of chaos. It takes a lot of work to keep your room or your house organized. And as you just use it on a normal basis, it tends to get more disorderly. So that's the concept of chaos. We're going to be looking at this spectrum of entropy. Here's the spectrum going from low entropy to high entropy. So high entropy is high chaos. So more entropy is more chaos. So we're going to have more chaos over here. And more disorder. And actually, things get into their simpler states. So imagine that you have all your books on your bookshelf. They're nice and they're organized, okay? That's sort of a state of complexity. And then imagine somebody coming over and bumping your shelf or knocking them down, and they just all fall all over the floor. So it's more chaotic, more disorder, but it's actually in the simpler state. It's in the state that they probably will end up in. I'll give you an example of that when we get to the water particles as well down here. Lower entropy, well, it's the opposite. The opposite of chaos is going to be order. Okay, the opposite of disorder is going to be structure. And the opposite of simple is going to be complex. So let's see how this applies to our three phases, the solids, liquids, and gases. Imagine a solid. Here's our particle model for solids. They're all nicely arranged in a regular 3D crystal pattern. So this has a lot of order, it has a lot of structure. Just think of ice with the hexagons, or think of sodium chloride with the alternating sodiums and chlorines. They're nicely patterned. Liquids, however, have a little bit more energy. We've melted the solid into a liquid, so they're kind of going all over the place, but they're moving and rolling around each other. Gases have the most energy, and these are going to be speeding all over the place. But these guys are going to be the most random. At least these guys kind of stick around each other. These guys are going to be off of each other and off the walls. Let's take a look at the example of water. And if we draw two water molecules looking like this, we're going to create these, take these two water molecules and we're going to create hydrogen and oxygen. You can do this with a little bit of electricity. Let's draw the hydrogens. We're going to end up with two hydrogens. Here's the two hydrogens. And we end up with one oxygen. So we have the two oxygens and we end up with four hydrogens like this. Well, here what we end up with is two particles over here. We end up with three particles over here. Count how many atoms that each of these has. Each of these has 3 atoms. So it has 3 atoms each. And then over here, you have 2 atoms each. So we have more orderly, structured, complex molecules over here because they have 3 atoms and they're broken down into smaller, simpler particles. So therefore, they have a higher entropy, more disorder. This over here on the left is more complex because it has 3 atoms per each molecule. Over on the other side, these guys are going to be simpler, or we can also say they're going to be smaller. So over here we have heat, we have exothermic, and let's actually cross this off right here, this increased entropy, or not cross it off, but we can actually just say this is going to be endothermic. So if you remember exothermic exiting, heat is going to be coming out. We took a look at exothermic and endothermic reactions. And endothermic means heat's going in. Our first example is going to be burning charcoal. So imagine you just have simple charcoal. Well, what you have in charcoal is carbon. It's just pure carbon. And you're burning that carbon in oxygen. What do you create? You create carbon dioxide, and you get lots of heat for your barbecue. Now let me show you an example of a non-spontaneous reaction. Can you take carbon dioxide, like the breath that you breathe out, add some heat to that, and get charcoal back and oxygen? I can write that reaction on paper. Does that mean that that reaction is going to occur? And the answer would be no. First of all, this is not a reversible reaction. Secondly, you just can't take these things over here and create this over here. So that would be an example of a non-spontaneous reaction going in reverse. Let's take a look at another example, and the example is going to be melting ice.